Okay, so let's continue. So just to recap where we are standing, we are talking about pulse amplitude modulation and how to design the transmitter pulse and the receiver filter impulse response in order to avoid intersymbol interference. So we will assume that we have done that from now on, and then we will talk about now how to implement the receiver. And if you recall back, what we're aiming at is to implement the minimum distance receiver. That is to pick the signal alternative which is closest to our observation. I will make this, of course, clearer as we go along. But before we start, first some recap of some important definitions: inner product, norms, and distances. So if we have signal x, if we take the magnitude square of that integrated for all time, we get its energy. The inner product between two signals, x and y, is defined as follows. It's x times y conjugate, integrated for all times. Then we get a number, right? And that number we call the inner product. And we had these funny looking braces in order to indicate the inner product. The norm, or we can think of it as the length of a signal, is defined notation-wise. We have double bars here, vertical bars. And it's the square root of the inner product of x with itself. Okay? And we know that the inner product of x with itself is just its energy. Okay? So it's the square root of the energy is the length of a signal. So we can think of this as somehow, do we think a signal is large or small? Well, it depends on its energy. And the energy then depends on the amplitude, but also on the duration. Right? So a signal with large energy could have high amplitude under a short time or low amplitude over a long time. Those have the same length, the same energy. Right? Of course, if it's a high amplitude over a long duration, it's even higher energy. The distance now, if we have a notion about length, we can compute a notion about distance. And distance is simply the length of the difference between two things. Okay? So the distance between x and y, capital D, x, y, is simply the length of x minus y. Okay? So if x is equal to y, for instance, then the distance will be 0. Makes sense? If x is very much different from y, then the different signal will be significant, and it would have a large energy, and the distance will be large. Okay? And mathematically, it's like this. Okay, the minimum distance receiver works on with these concepts. And remember that the receiver, what it does, it takes an observation of the received signal and try to figure out what was the transmitted signal. The transmitted signal could be one out of capital M possible signals. These are the signal alternatives. And then what we do is simply compute the distances between the received signal and the Lth signal alternative. And we compute that for all signal alternatives. All right, and then we have a bunch of distances. And our choice, our decision, will be based on the signal which has the smallest distance to the received signal. So we're looking at the transmitted signal, the signal alternative, which is the closest match to what we have received. So what we are looking for here is m hat, which is the index of the signal alternative we think has been transmitted. Okay, it's arg min of dl, and dl is these distances. So if we plot them, we have for 1, 2, 3, 4 in this case, so capital M is equal to 4. And we plot that as a function of L. And then we search among those until we find the minimum distance. We don't care about the value, what the minimum distance is. We only care about its index. It's L, if you like. And that is what we call m hat. Okay. So now it's absolutely crucial that we understand this notation, that arg min of D does not mean the minimum distance per se, but the L that corresponds to the minimum distance. Okay? Right? So we search among our distances, we find the smallest one, and we read off this value. We don't care about this value. We only care about this one. If we have this, we have a implicit guess on what was the transmitted signal. And if we do that, we can map back and get our bits. Okay? As we will see later on. Okay, so this is the definition of the minimum distance receiver. We select the signal alternative which is closest to the received signal. Instead of working with DL, where we have the square root, we can avoid the square root by just squaring DL, and we would get the same decision here. Right? Since we are not looking for the minimum distance or the minimum distance squared, but rather to the L, which is corresponding to the minimum distance, there is an equality here. Okay? Question?
Can you clarify the notation of the arc just of positive argument?
Yeah, why it's called? Okay, so the question is, why this funny notation? It's because if it's like this, it's only the minimum. That's this value here. So the minimum distance, whatever it might be, 16 or 32 or whatever it is. But we don't really care about that. We only care about the index to this minimum distance. So the minimum, the L is what we're looking for. So if we look at this as some function which minimizes this over this argument, the possible L's, and argmin just simply picks out the smallest distance, the index to the smallest distance. So it's really important that we have that clear to us. So thanks for the question. So, I mean, I'm happy to explain this until we all understand this. So are we okay with this notation now? Right. Okay, so we're gonna manipulate these type of expressions now quite a lot. And if we don't understand this, chances are we won't understand much of the other stuff then. Okay, so we compute the distances, we select the smallest distance, we find the smallest distance, and then we read off the corresponding index to this. That's what we're looking for. That's the procedure. Okay, and just to be absolutely clear that we can go from here to here, okay, so suppose I plot here along this axis D, the distance, the different distances. So suppose for simplicity we only have two distances. Say D2 and then D1 here. Okay. So if this is the case, what is our decision? 2, exactly. So we read off the index of the smallest one. Okay, and this is clearly smaller than this one, right? Okay. Now, if we plot on this axis D squared instead, we of course have the square function like this, and then we have here D1 squared, sorry, D2 squared, and D1 squared. Okay, so if D2 is less than D1, for sure D2 squared is less than D1 squared, right? So this proves this step. Okay, we can do other things also. So if m hat is the arg min over L of dl squared, this, I claim that this is equal to this also, that if we take dl squared here and we compare those with each other to find the one with the smallest, the smallest of those and pick the index of that. Of course, I can add a constant to this without changing anything. Agree? Because it's basically just taking these and we just add the same number to all of these. We're still going to pick up the smallest one, right? So we can add and subtract any constant here to this function, and we still have equality here. Okay, we can also multiply this one with any constant as long as this constant is positive. It simply means that we multiply all these numbers with the same thing, and the order of them in magnitude is preserved. Okay? So this is true for any constants A must be greater than 0. Okay? Otherwise we flip everything, that's not good. And B. That does not depend on L, of course. I mean, this cannot be a function of L, because then things are different. Then we multiply the different distances with different numbers, and who knows what's happening, right? Same thing, B cannot depend on L, because then we add different numbers to the different alternatives. That doesn't work either. Okay. Are we okay? All right. So, the book in which all this, the theory that we will talk about now, it's this Barry Lee and Messerschmitt that you find on the library in electronic form. So in this chapter 5.3.1, they make a change of notation through, in the middle of the chapter. And to be consistent with the book, we'll also make the same change of notation. So I apologize for this because it's a little bit confusing. But instead of being consistent with notation and not use the same notation as the book, or to use the notation of the book, I chose to be consistent with the book. Okay. So we're going to make a change of notation. So this is the block diagram we will consider now. The only difference is that instead of G, we now say H here. Okay. So that's the difference. Okay. So then the Nyquist criteria has to do with H convolved with F, rather than G convolved with F. What makes this bad is because previously H was G convolved with F. I didn't write the book, what can I say? Okay, but that's what they did. Okay, so transmit pulse now, from now on is H, and it used to be G. For ISI-free transmission, we're going to look at H convolved with F, and that should be a Nyquist pulse. And we will simplify things a little bit here now. So we will say that it's a scaled Nyquist pulse is okay, which means that if we take t-spaced samples of this, we get 0 for all samples except when k is equal to 0, and then we get a constant, which is non-zero. Okay. All right. Now, so what we want to do here is to, first of all, talk about the receiver filter, and then talk about this box, so that what we get out here corresponds to the minimum distance receiver decision. That's what we want to do. And to do that, we do that in 2 steps. First of all, we look a little bit about this step and then try to characterize what y is. And once we have done that, we can figure out how to design this one. So we'll take this in 2 steps. Okay. So, how to select F? Well, I already told you earlier that one way to select F, which is very commonly used in practice, is to use F as being a matched filter. And a matched filter needs to be matched to something, obviously, and it should be matched in this context to the transmitted pulse. Okay, so it should be matched to H. So F should be selected to be matched to H. Okay, and what is matching? Well, we just say that F is equal to H conjugated and time reversed. That's it. Okay. So we will use a matched filter. So the impulse response of the receiver filter F is equal to H conjugated and then time reversed. Good. Then a matched filter can actually be used to compute these inner products. What inner products? These inner products. Okay. So now we will see that the output of the matched filter corresponds to an inner product. Not because we know why that should be good, but trust me, it will be good. Okay, so a matched filter can be used to compute inner products because if R here is filtered through a matched filter which is matched to h and y, and then we sample at time equals to 0, the output sample y, that is y at time 0, is equal to the inner product of r with h. Okay. Let's see why that is the case. So y, this number, is y of t when t is equal to 0. Okay? So this is y of 0. Okay? And what is y? Y of t is simply r convolved with the impulse response of the filter, which is h conjugate negative t. Okay? This is a signal. Convolution between two signals produces a signal. And then we sample that at time equals 0. And that gives us the output sample. Okay. So let's expand the convolution or write it in its integral form. So it's simply an integral from minus infinity to infinity of r and then h. Okay, and let's stop here for a moment. I got ahead of myself. So before we put in this, we put f of t here, sorry. Okay, and now I would like to talk about convolutions. Many people don't like convolutions. I think it's unfair to convolutions. They're very nice, very good to know, and they're not so difficult to figure out with some just basic rules on how to write up the integrals here. The first thing we need to figure out is that a convolution is a signal, okay? So if we convolve two signals, we should get a signal and it should be a function of time, okay? So there must be some t dependency here, and then we also need to integrate. So we need to figure out an integration variable, and we need to have a t in the integrand, and that t should survive the integration. So the integration variable we choose here could not be t, could be anything else. Can I get a suggestion for a letter not equal t?
Tau.
Tau. Many people like tau. Okay, so we're going to integrate over tau, or u, or v, or whatever, right? But not t. Then we need to figure out what the arguments of these two things should be. And one of these should have the same argument as the integration variable. We can select which one we like. Doesn't matter. So whatever is convenient, we can pick tau here or there. Doesn't matter. Let's put it here. Let's hope that this is what I did also. Okay, yes. And then the other one, what should that be? Well, first of all, it has to be a function of tau, the integration variable, and it also has to be a function of t. Okay. And it should be in the following form. It should be t minus the integration variable, tau. Okay. So as long as we keep track of these simple rules, that the integration variable should not be t, and we can put the integration variable in either of the arguments, and in the other argument it should be t minus the integration variable, then we're home free. We'll never fail. Okay. Okay, so now we have this. And now we wanted to evaluate this signal. This is a signal, it depends on t, and we want to evaluate that at time 0. So let's put in t equals 0 into the integral here. And then we have integral from minus infinity to infinity r of tau, f minus tau. Tau. Why is this true? Well, it says here, put in small t equals to 0, and I did. Okay, and we did. Now, if we have a matched filter, then this part here is related to h. How is it related? We know that f of t is h conjugate negative t, but here now is a function of tau, so we can replace t with tau here. And then we simply see that this is h conjugate. Instead of negative tau, it will be tau. Right? Because, yeah, just use this equation and replace tau with tau, t with tau, and conjugate the left-hand side and right-hand side. And we're there. Okay, so this is simply the integral from minus infinity to infinity of r tau h conjugate tau, the tau, like this. Okay. So if we go back here, we see that this integral is of this form, where we have a signal multiplied with the conjugate of that signal and then integrated for all time. Now, instead of t, it's tau here, but it doesn't matter. You can choose the integration variable to whatever you like. So this is simply the inner product of r and h. Okay. Good. What else can we say? If r happens to be h, what can we say about y then? Any suggestion?
Magnitude r squared in the integral.
Yeah, it would be magnitude r squared here in the integral, and r is equal to h, so it's going to be magnitude h, and when we integrate that, we're simply going to get the energy for h. Okay, so we will use this later on. Okay. Okay. So, we will soon prove this, but I will tell you the end result. Is that we want to do a minimum distance receiver, and I claim we can do that by just having first a matched filter, where the impulse response is matched to the transmitted pulse. We sample that once every with symbol rate, which means that we take a sample for each new symbol being transmitted. We take one sample. The output of this, we multiply that with 1 over EH. Okay, so this is a amplifier with this amplification gain. And the gain is 1 over EH, so EH raised to the negative 1. Okay, it's 1 over EH. And then we get Z, and then we feed that through this box here, and out we get the decision. This is the claim. Okay. This part to the right here, with this funny looking symbol in it, is known as a slicer. And what it does, it takes the input and compare that with all the values in the symbol alphabet, curly A, which is the set of possible transmitted amplitudes, and then output the amplitude which is closest to Z. So sort of minimum distance receiver, but only working on amplitudes now. Okay. And the claim is that this is a minimum distance receiver if we are using a system that does not have intersymbol interference. So when H convolved with H conjugate negative T is a scaled Nyquist pulse. That is that this condition is fulfilled. Okay. Right. And this is true when H is a root Nyquist pulse that we started with in the first hour of the lecture today. Okay. All right, so let's prove this now. Because if we do, we know how to build actually the best best receiver for pulse amplitude modulation. Okay. We know here that we're going to transmit symbols in a stream of symbols. So we will get a new amplitude every t seconds, and then we will multiply that with a pulse and transmit that over the channel. So what we will do now, first of all, is that we try to decode just one of these symbols, namely that one where k is equal to 0. So we can think of this as being the first pulse that we transmit over the signal. So we'll see how we can decode that with the minimum distance receiver. And when we know how to do that, we can simplify, we can easily extend that to take care of decoding any other symbol where k is not equal to 0. But we will start with k equals 0. And this is known also as the one-shot receiver. Simply, we transmit one pulse, and we want to try to detect that as best as we can. So we want to consider the transmission of a single pulse. Okay. So we transmit the pulse when k is equal to 0 is just A0 is the amplitude, and it carries a number of bits. And then we multiply that with the pulse shape g, and we just transmit this over the channel. Okay. So this is what we have transmitted. So A0 here can take on a certain number, a number in this set, curly A. And curly A is the set of amplitudes A1, A2, up to A capital M. Okay. So we don't know what A0 is, but we for sure know it's one of these amplitudes, which is a predefined set of amplitudes. We just need to figure out which one. Okay, so this means that the transmitted signal alternative with index L, okay, so this is the Lth possible transmitted signal alternative, is simply AL times G of t. So the Lth signal alternative, we get that by putting A0 equal to AL. Okay, well, I'll take that once more because it's important. We transmit the single pulse with the symbol A0 times G. We don't know A0, right? That's the problem. So the receiver needs to figure out what is A0 or make a guess of that. What do we know by A0? Well, it could be one of these amplitudes. We don't know which, but it's going to be one of them, right? What are the possible transmitted pulses then? Well, they are indexed by L, where we take the Lth of these amplitude and multiply that with G. So what we want to do is to compare the received signal with all these possible ones, and then pick the one which has the best fit. Okay, so that's the minimum distance receiver. Okay, great. Okay, so we want to compute these distances, and actually we want to compute the distances squared because it's It's just a lot of work writing square roots all the time. So we want to compute the dl squared, and that's simply r minus SL magnitude norm squared, so like that, by definition. Or in integral form, it is the integral from minus infinity to infinity of r minus the LF single alternative, which is AL times G. Sorry, I ran out of board there. Okay, so we just have to compute all these integrals, right? And to our help, we're going to show that we can actually do that by using the samples of the matched filter. Okay, so that's what the goal here. Now, so what we want to do is we want to simplify this integrand into a form that we can identify the output of the matched filter as part of that. Okay, and to do that, we do a little bit of a detour here and consider the following equation. We take x minus y magnitude squared, where x and y are complex numbers. So what is this? Well, it's x minus y times x minus y conjugate. Okay. The magnitude squared of a complex number is the number multiplied with its complex conjugate. Okay. Then we continue here and multiply these together. So we take the conjugation inside the parentheses here. So we get x conjugate minus y conjugate. And then we multiply everything together. And then we get x times x conjugate minus x y conjugate minus y x conjugate minus, so that's plus y y conjugate. Okay? We can write this as x magnitude squared, the first term, and then we take the the cross terms and we write the parentheses around that. So it's negative x y conjugate plus y x conjugate plus y magnitude squared, like this. Okay, so far? Okay. So what do we have here inside the parentheses here? Well, we have x y conjugate plus y x conjugate. And y x conjugate is y conjugate, it is equal to x y conjugate. I'm going to mess this up again. Okay, I'll start over again. Okay, we want to write this in terms of this. Okay, so we almost have it, except there is a conjugation missing here. So we just write this as x, y conjugate, and then conjugate the whole thing. And we see here that x, y conjugate conjugated is x conjugate y, which is exactly what we had up here. Okay. Okay, so here we have a complex number plus its complex conjugate. So what is that in terms of real parts and imaginary parts? A complex number plus its conjugate is
A real number?
real number equal twice the real part of it, right? Okay, so this will be 2 times the real part of x, y conjugate. Okay. Now, so here we have x minus y magnitude squared. So let's put in x equal ROT and y equal ALGT. Okay, and then we simplify the integrand here. So dl squared, that's what we're looking for. And what is dl squared? Well, it's this integral here, like this. And then we know that we can simplify the integrand according to this formula here. So we simply have this as the sum of three integrals. The integral from minus infinity to infinity of the first term magnitude squared, which is r of t magnitude squared dt, minus 2 times the real part of an integral from minus infinity to infinity of r, let's see, r is equal to x and y is equal to al gt. So here we will have al conjugate gt conjugate, like this, dt. And then plus the third term, which is the integral of the magnitude squared of the second term here. So it's going to be an integral from minus infinity to infinity of al magnitude squared times g magnitude squared dt, like this. Okay, so the only thing I've done is to take this integrand here, using this equation, expanding it into three integrals. Okay. Let's look at the first part here. So what is this in terms of energies? This is equal to the energy of
R.
Exactly. We take r magnitude squared, integrate for all times, we get the energy for r. Great. Then with and let's see, this thing here, if we take out al conjugate and put that outside the integral here, we have the integral from r times g conjugate t dt, and that is the inner product of r and g. Just replace this integral here with this integral here. Okay, and al is just a constant. I put that outside the integral, and I have to keep the 2 times real part of this. Okay, and the last part here, we'll just pull out al magnitude squared because it's not a function of the, well, it's a constant essentially. And then we have the integral of g magnitude squared for all t. So what is that in terms of energies? It's the energy of, right. So here we have the energy of g. Now this inner product here with r and g, I messed up greatly here now because I've been using g all the time where we should have used h. Remember that? I said that we changed notation and I didn't do that on this board here. So let's now change that in the last equation here and change all the g's to h. My apologies here. Okay, so it's going to be er, r, and then h and h, the energy of h. Okay. Now, what we see here, we have then the inner product of r and h. Have we seen this before? Yes. Okay. So it's the sample of the matched filter at when we sample at time 0. Okay. So this is what we call the y, where y, to be precise, is this number when k is equal to 0. Okay. It's the inner product of r with the pulse to which the filter is matched, and the pulse to which the filter is matched is H. So the output here, when we sample, will be the inner product of R and H. Okay, so here we have Y, so that's good. So now the matched filter came into the equation here. Okay. And now we're just going to use a few, manipulate this a little bit. And it's not completely obvious why we do this, except that the end result becomes nice. Okay, so for some reason I decide now to break out EH. So it's going to be EH times parentheses ER divided by EH minus 2 times the real part of AL conjugate times Y divided by EH plus 1. Sorry, AL magnitude squared. Okay. And for no particular reason, except that the end result will be nice, let's look at some other equation here, where we take Y divided by EH, and then subtract off AL, and take the magnitude squared of this. And then we use the same formula as we had before, when we have x minus y magnitude squared. Now we have x is equal to this, and y is equal to this. So this is going to be magnitude y squared divided by EH squared minus 2 times the real part of the first term, which is y divided by EH times the complex conjugate of the second term, which is AL, and then plus the magnitude squared of the second term, which is AL magnitude squared. It's just algebra. There's nothing magical about this. The good thing, however, by doing this is that we see that inside the parentheses here, we have something that looks very similar to what we have here. As a matter of fact, the last two terms here is equal to the last two terms here. So what we do here is to replace this box with what we have on the left-hand side here and subtract off this. Okay, so it's just algebra. Oh, I hate that. Okay, we're still computing the magnitude distance squared. And then we see that this can be written as EH. I need to retire that. EH parentheses ER divided by EH. And instead of the yellow box there, I write this expression, which is Y divided by EH minus AL magnitude squared, and then subtract off the missing term here, which is Y magnitude squared divided by EH squared. Okay, and now multiply EH into this parenthesis, and then we are almost done. We get ER plus Y divided by EH minus AL magnitude squared minus Y magnitude squared divided by EH. Okay, so we have done a lot of manipulation to figure out what the distances squares are. And now we have arrived to a nice expression, I claim, where in this expression we have the energy of the received signal. We have Y, which is the output sample of the matched filter. We have EH, the energy of the transmitted pulse. AL, which we know. And then Y again, and EH here. And what is the thing? We want to find M hat as being the arg min over L of DL DL squared, right? That's what we're looking for. Okay, and now we have an expression put for DL squared here. And then we see that the first term here, does it depend on L? No, it's the energy of the received signal. It does not depend on L. So this is independent of L, right? The second term, the third term here, does it depend on L? No, it's just the Y magnitude squared divided by EH. So these two terms, they don't depend on L. So we can ignore them when we're trying to find the best L. The middle term, however, very much depends on L because we have L here. Okay? So M hat is simply the arg min over L, where we have Y divided by EH minus AL magnitude squared. Okay, so after a lot of manipulation here, we have gotten to a result where we can see that the minimum distance receiver for PAM can be computed as follows, right? Arg min of this. Okay, so what is inside here? Well, here we have the matched filter sample. That's Y. Okay, so that tells us that is all we need to know about the received signal. It's in there, right? EH is a constant. It's the energy of the transmitted pulse. We know that. AL, we know what the different ALs are because that has to do with the possible signal amplitudes. This is a design choice. So we're done. That's it. Okay, so let's see how this is actually in the block diagram here. First of all, we take R, matched filter, then we get Y, and we sample it, and then we get Y. Then we divide by EH. We take Y, divide by EH. So Z here is this first term. Okay. Next thing we do is we feed that into the slicer, and we find the A in curly A, which is closest to the input. Okay, that is, we compare Z with all the possible A's, take the differences, magnitude squared, and then output the best of those. Right, we're done. So this is the minimum distance receiver for PAM, right? And it's quite simple in its structure, right? We don't need to do a lot of integration and so forth. The only thing we need to do is to implement the matched filter, sample it accordingly, and then process the samples by just dividing with a constant, and then looking at these samples and compare them to the possible amplitudes and pick the best amplitude, and then we're done. All right. 4 minutes after the hour. Okay, so sorry for taking that of your free time. So we'll see each other on Thursday, and then we'll continue from here.